Most stars in our galaxy are small, cool M-dwarf red stars. These stars are dim, but they burn for trillions of years, making them promising for life. Planets must orbit very close to an M-dwarf to stay warm enough for liquid water. This close orbit puts the planets right inside a dangerous orbital trap called tidal locking. Tidal locking is common for moons, but for a planet in a habitable zone, it creates an extreme climate challenge. We will explore why M-dwarf systems present a dark side to the search for alien life. Now, to define the habitable zone, or HZ, first, we need the central star's energy output. The habitable zone is the orbital distance where a planet with an atmosphere can sustain liquid water on its surface. For our Sun, the HZ is wide-spanning, from the orbit of Venus out past Mars. M-dwarfs emit much less energy, so their HZ is very narrow and sits extremely close to the star. For example, Proxima Centauri, a red dwarf, has a habitable zone, a tiny fraction of an AU from the star. Such a close orbit ensures the planet receives enough energy to warm its oceans. By contrast, this very tight orbit is also the primary mechanism for strong tidal forces. Let's examine tidal forces, which are caused by the gravity gradient across the planet. On the day side, the star's gravity pulls strongly on the planet's near side and weakly on the far side. This difference in gravity creates a bulge of solid rock or liquid on both the near and far sides. As the planet rotates, the star pulls on these bulges, trying to slow the planet's rotation. Over billions of years, this constant tidal braking gradually slows the planet's spin. The braking stops only when the planet's rotation period matches its orbital period. At this point, the planet is tidally locked, meaning one hemisphere permanently faces the star. The planet now has an eternal day side and an eternal night side, split by a narrow terminator line. The time to achieve tidal locking is short, for close orbits taking perhaps just 100 million years. Now we use a diagram to see the extreme effects of this permanent day-night split on the climate. On the diagram, the day side constantly receives intense stellar radiation, heating it to hundreds of degrees. The night side permanently faces away, leading to a catastrophic drop in temperature, perhaps below -100 degrees Celsius. If the planet has no atmosphere, the night side's water and atmosphere will freeze and migrate away. The planet's atmosphere is its only hope to evenly distribute heat across the planet. The high temperature difference between the day and night sides drives fierce atmospheric currents. Air heated on the day side rises, then rushes violently towards the colder night side at hurricane speeds. This super rotation of the atmosphere creates a powerful jet stream, moving heat pole to pole. On the diagram, the intense wind can carry enough heat to warm the planet's night side slightly. But the fierce winds also create a permanent thick cloud layer over the day side called the substellar point. This constant cloud cover reflects stellar energy, potentially cooling the day side below the freezing point. The resulting climate is a harsh battle between heat migration and cloud reflection. In cross-section, the day side's clouds are thicker and higher, reducing solar energy input to the surface. If the atmosphere is too thin, the night side collapses and freezes and all water is lost. If the atmosphere is too thick, it traps too much heat, leading to a runaway greenhouse effect. The amount of carbon dioxide in the air and the speed of the winds are crucial for habitability. In cross-section, deep ocean currents also move heat, but much more slowly than the atmosphere. The ocean circulation pattern involves warm water moving along the surface to the night side before sinking. Deep water then returns to the day side where it is heated again, continuing the cycle. The combination of wind and ocean currents defines the planet's final climate state. Now let us look at some theoretical examples of these tidally locked worlds. An eyeball world is one possibility where a small ocean exists only in a narrow zone near the substellar point. The perpetual day side is a boiling desert and the night side is frozen solid with thick ice. Only the temperate ring or eyeball of liquid water along the terminator can possibly host life. Another possibility is a water world covered by a single global ocean. In this case, the ocean currents distribute heat more effectively, perhaps preventing a full night side freeze. The most extreme case is a deep, thick atmosphere where the heat is almost perfectly distributed. This super-rotating atmosphere can lead to temperatures that are relatively uniform across the entire planet. However, the constant super-hurricane winds near the surface make complex life highly unlikely. The third possibility is a planet with an extremely low mass or no atmosphere at all. This results in a frozen world with a molten day side where the only liquid water is in the atmosphere. The fourth possibility is a cold trap world where the night side atmosphere freezes out and collapses. This creates a constant cycle where the atmosphere is slowly depleted and deposited on the night side as ice. Kepler 186f is one of the first near-Earth-sized planets found in a red dwarf habitable zone. Kepler 186f is slightly larger than Earth and orbits its M-dwarf star every 130 days. Because of its close orbit, it is highly likely tidally locked into a permanent day-night configuration. The planet's habitability hinges entirely on whether it has an atmosphere thick enough to circulate heat. Scientists are also studying TRAPPIST-1 system with 7 Earth-sized planets all close to a red dwarf star. All 7 TRAPPIST-1 planets are almost certainly tidally locked, creating a complex set of climate challenges. These 7 planets offer a natural laboratory to study the different outcomes of tidal locking. From above, we see the compact arrangement of the 7 TRAPPIST-1 planets orbiting their central star. The innermost planets receive too much stellar energy, while the outermost may be too cold. Only the middle 3 planets, TRAPPIST-1, E, F, and G, are thought to be in the tradition H, Z. The high magnetic activity of M-dwarf stars is another problem for habitability. M-dwarfs frequently blast out powerful stellar flares that can strip a planet's atmosphere away. These flares are intense pulses of ultraviolet and X-ray radiation that can erode an atmosphere over time. Tidally locked planets may need an extremely strong global magnetic field to protect their atmosphere. Now let us summarize the challenge of tidal locking and the resulting climate extremes. Tidal locking results in a permanent day and night split, which leads to extreme temperature differences. This temperature difference drives fierce super-hurricane winds across the planet. These winds carry heat, but also create permanent thick cloud cover over the substellar point. The resulting climates range from cold traps to eyeball worlds to uniform hot planets. Habitability is a narrow window requiring a perfect balance of atmospheric thickness and ocean currents. The existence of liquid water on these worlds is possible, but life would face extreme challenges. Now we shift to another effect, the planet's gravitational interaction with its star. Because the planet is so close, its gravity strongly affects the star, creating two tidal bulges on the star. On the diagram, the planet's gravity pulls on the star's photosphere, causing it to slightly distort its shape. This tiny distortion is known as the stellar tidal bulge, which also slows the star's rotation over billions of years. The tidal forces also damp out the planet's eccentricity, making the orbit perfectly circular over time. A perfectly circular orbit helps stabilize the climate, further reducing temperature variations. The planet's orbit can also be forced into a mean motion resonance with other planets in the system. This orbital resonance keeps the orbits locked into simple integer ratios, preventing them from colliding. From above, we see the orbital path of two planets locked in a 2-to-1 mean motion resonance. While tidal locking seems to kill habitability, it also creates a unique type of Earth-like environment. Life forms on a tidally locked world would evolve to exist in a narrow temperate terminator zone. The life would need to survive constant winds and an eternal sunset environment. By contrast, life on the day side would need to tolerate extreme heat and constant light. Life on the night side would need to survive deep cold and perpetual darkness, perhaps using geothermal. The potential for life in these systems is higher because M-dwarfs last for an extremely long time. M-dwarfs live for up to 10 trillion years, giving life vastly more time to evolve than on Earth. This extended lifetime may outweigh the climate challenges of tidal locking. The long-term stability of the M-dwarf star may allow life to survive the initial violent tidal locking phase. Scientists are designing the James Webb Space Telescope to directly study the atmospheres of these worlds. Webb will measure the composition and temperature of exoplanet atmospheres, looking for signs of heat circulation. The light from the M-dwarf star passes through the planet's atmosphere, revealing its chemical makeup. If a tidally locked world shows a small temperature difference between its day and night sides, it indicates a thick atmosphere. This small temperature swing would be a major clue for the potential habitability of the planet. The goal is to find biomarker gases like oxygen or methane in the planet's atmosphere. But a tidally locked planet's oxygen may be from water vapor broken down by stellar flares, not life. That's why we need to understand the complex physics of tidal locking and atmospheric circulation first. From above, we observe a small planet orbiting its M-dwarf star, highlighting the close orbital distance. The orbital path is highly circular due to the strong tidal forces reducing eccentricity over time. The red star's output is low but consistent, allowing for trillions of years of stellar stability. This stability makes M-dwarfs the most common and longest-lasting hope for finding alien life. Now let's revisit the concept of an eyeball world one last time as a potential haven for life. The terminator zone of the eyeball world is the only place where liquid water can exist. It is a permanent twilight environment with relatively moderate temperatures. Life forms could thrive here, avoiding the frozen night and the scorching day. The challenge is the constant hurricane force winds that sweep across the surface of the planet. This means any life would need strong anchors or exist primarily underground or in the oceans. The deep ocean may hold the key to life on tidally locked worlds, protected from surface extremes. The possibility of geothermal vents on the outside could provide energy for deep ocean life. The search for life in the galaxy is heavily dependent on understanding these tidally locked worlds. About 70% of stars are M-dwarfs, making this planet extremely rare, not the exception. The dark side of the habitable zone is a scientific challenge we must solve to find our cosmic neighbors. The physics of tidal do not crucible for life, forcing it to adapt to extremes. Future telescopes will refine our understanding of these worlds and narrow down the best candidates. The next great discovery of life on the planet permanently orbiting a red dwarf star.